vote of thanks for the inauguration of this 6 days online FDP on advanced trends in renewable energy systems and smart power technologies. First of all, I would like to express my sincere gratitude to our principal, Dr. S.P. Subramanian sir, for your valuable time and for inspiring us with your brilliant inaugural address. You have set the perfect tone for this program. Also, I express my sincere thanks to Professor Sushma ma'am and our resource persons Dr. Nafeesa K and Dr. Sobha Manakkal. I express my thanks to our head of the department, my fellow coordinator Ms. Archana P, and all the faculties of Triple Department for their hard work in bringing this event together. Finally, thank you all the faculty members, research scholars, and professionals who registered. Your overwhelming response is what makes this event possible. We hope these next 6 days help everyone learn, connect, innovate, and transform. Thank you all very much.
Thank you, ma'am.
By this, we can wind up the inaugural session. Now we can move to our first session of this FDP. It gives me great pleasure to introduce our distinguished resource person for this session, Dr. Nafeesa K, Professor and Head of the Department Triply at MES College of Engineering, Kuchipura. Dr. Nafeesa K has extensive academic and research experience in the field of electrical engineering. She has a doctoral degree in the field of optimization of the starting performance of three-phase AC voltage controller fed induction motor from NIT Calicut. She has more than 25 years of academic experience. Today, she will be delivering a session on the topic Power Converters for Renewable Energy Systems, which is highly relevant in the context of sustainable energy integration and modern power technologies. We are delighted to have her with us and look forward to an insightful and enriching session. On behalf of CIMAT, I extend a warm welcome to Dr. Nafeesa K and invite her to begin the session. Thank you, ma'am. The session is yours.
Thank you. Thank you. 1 minute. Let me share my screen. I'll join from my phone. Am I audible, right?
Yes, ma'am.
Screen is visible, right?
Yes, ma'am. Visible, ma'am.
Okay, thank you. Good evening, all. The topic of the presentation is power converters for renewable energy systems. Actually, this topic is, we know that this in today's world, all are talking about sustainability, renewable energy, EV, and all, always talking about green energy, clean energy, and all. And the goal is to have a sustainable world. And actually, this topic is covering the basics of converters. And I hope the participants are from different fields, from different branches and different areas of electrical engineering, and those are already in power electronics area. Sorry that I am covering the very basics also. So let me move directly. And also, we know that we have 2 sessions in this day, and so I will try to finish it as early as possible because sitting too much in the evening is also, I know it's also difficult for the all participants. And I will, these are the contents of the presentation. I have arranged the topic like this. First, we will cover, just because this is the first session, I will just uh, quickly run through what are the renewable energy, different renewable energy systems, and what are the need for power electronic converters, then fundamentals of power electronics, different converter topologies, then inverter topologies, solar PV conversion systems, then wind energy conversion, then battery energy storage, and then the conclusion. And coming to the introduction, as we have already mentioned, the sustainable field, sustainable world as the point of interest. So for that, we need power electronic converters, and these power electronic converters play a crucial role in bridging this gap by enabling an efficient conversion, then voltage regulation, maximum power point tracking, synchronizing the grid, and improving the power quality. So the importance of power electronic converter is very essential. So, and coming to the and before going to the area, we'll just quickly go to the current status of the power generation and the global status. And this data is taken from the internet, and this data is in 2024. See, here coal is giving 35%. Even if we are talking all the world, all the globally, we are talking about carbon neutrality, sustainability, and still the coal is having 35%, and this is not at all environment friendly. And next gas is 22%. So see, the global status is we are having wind only 9%, and solar is only 6%, and the other sources are also shown here. And see how very less penetration of the renewable energy sources are seen globally. And coming to the Indian status, see, this is the generation installed capacity. And see here, India is somewhat better. But the call percentage is 42 point. Call percentage is more. But as on renewable status, we see solar penetration is more in India. It is coming to be 27%. But from the global, it's only having 6%. So, but still the call ratio is high. Call percentage is high, 42.5%. And we are all talking about carbon neutrality and maximizing the renewable energy and protecting our environment, all these things. And so see, wind is only 10.5%, and all the other sources, biomass, nuclear, and all are shown here. And coming to the Indian renewable energy mix, and this is actually the data in 2026. The sea solar power is 68.05%. That is very good. So, and we know that in Kerala also the penetration of the solar is very high, and the geographical area and the availability of solar power is very good compared to the wind. Wind potential is very less in Kerala. I mean, the wind velocity, that means the possible wind velocity to convert into the electric. That's why the solar is more in penetrating to the sea. And coming to the different non-conventional energy sources, we know solar, wind, bioenergy, ocean, geothermal, these are all contributing to the renewable energy sector, solar energy, and this is mostly used. Actually, all these energies are coming from sun. And then we have wind energy. Actually, the kinetic energy associated with the large masses of air is converted into electricity. and this is generally used in agricultural and rural and municipal uses, pumping agricultural tree pumping applications. Then large scale electricity generation is also doing by this wind energy, and then biogas. And this using this biogas also, it's from organic materials, from waste, biomass is produced, and then biomass, this is also used to generate electricity. And using the biogas, that biomass that is actually obtained from the biological waste of the plants and animals. And then ocean energy, and this we have tidal and wave energy. So these are different possibilities of getting renewable energy from diverse sources. And then why as power electronics? I mean, why an interface is required? We know that the energy generation, and if you're talking about solar energy, we know that solar is available. It's not available throughout the day. Like the intensity of the solar radiation is also varying, isn't it? So, like in the morning, you will be getting very less power and very less voltage, but at the noon, we'll be getting very high voltage. And the voltage generated from this source may not be, we cannot give the source directly to our load, isn't it? We cannot give this to directly to our lighting load, fan load, or motor load. So what we require? We require a conversion. We require a power electronic converter to convert this energy into the energy or the voltage required by the load. See, all the loads are generally designed, or it is having a rating. Like in our fan, there may be ratings are marked, like it is having a voltage requirement, current requirement. Uh, and that source has to get that voltage and current to operate in the its normal operation. And for that, even if your voltage source available voltage source is a DC source, but the fan which is running in our home as an AC fan, so it require AC voltage. So what we should do? We need to convert this DC into AC. So that is the requirement of the that is the requirement of the interface. So we need to interface source and load. And so what we have, what are the different functions we need? Voltage regulation, then frequency frequency conversion may be required. Then sometimes AC to be converted into DC. If our load, if the motor is a DC motor, we need to give a DC supply. So, but the available voltage is AC source, then we need to convert this AC into DC. Then we will use inverter. Similarly, sometimes we need to convert it in DC voltage into AC voltage. Then maximum power point is to be tracked from the solar plant, and then grid to be synchronized. So if you are generating a voltage, if you are generating a power from your power plant, solar power plant, and if you are injecting this power into the grid, and that should not be directly connected to the grid, right? So you need to we need to synchronize it. We need to equate the voltage, phase sequence, frequency, and all. And for all that, we need an interface. Then, if you are introducing your power electronic circuits into the power system, into the grid, what is a major concern? It will produce harmonics, right? So, thus, harmonics reduction technique has to be incorporated for that also. Then power flows to be controlled. And if we are talking about a grid connected solar plant, power flow, it has to be flow from the plant, our plant, to the grid side, or from grid to the our plant, I mean our home, and all these things. Then protection, if you are using all these things, protection to be ensured, then isolation is to be ensured. See, all these things are coming under the interface between the source and outside. Okay, and this just shown a figure to show that this is a solar PV, wind turbine, battery, and we have a DC bus here. So if it is a PV, we know that it is a DC voltage. And this DC to be, this power electronic, this DC cannot be directly used. So it has to be converted as required. And this is given to the DC bus. Similarly, if you have a wind DC bus, wind turbine is there, windmill is there, and that has to be converted. Battery voltage and power voltage requirement may not be same as the DC bus, so you need to use a converter. And if our load, home load is AC load, then you need to convert this DC to AC in that way. So in that way, interface is required. Similarly, different challenges with this intermittency. We know that the power wind may not be always available, solar power may not be always available. That is why it is called an intermittent source. So we need to use energy storage, then voltage variations. So we need to have voltage control converters. Then frequency may not be in windmill and all. Frequency may not be as required by the load. So need to convert that also. Harmonics ought to be reduced. So for that we may need to use filters or advanced PWM techniques has to be used. Grid synchronization to be used. That make, for example, can be done by PLL control, and that showing a bigger picture with the different sources and interfaces shown in the right side. So this we know that without power electronics, large scale integration of renewable energy is not possible. So this converter should operate with efficient energy conversion, efficient power flow. It should have grid integration, power quality improvement, all that should be incorporated into the system. So for that, we need power electronic converters. And if we know that it should be operated in high efficient way, reliability should be there, fast switching speed should be there, power quality already mentioned, it should be compact and lightweight design. So for the converter, we need to use different power electronic devices, right? And this is just I have taken from this GAN power site, like the evolution history of the the evolution of the power electronic switches. In 1952, we have power diode. Sorry. Then 57 thyristor came. Then BJT, MOSFET, IGBT, Schottky diodes. Then the recent high efficient devices introduced in 2010 as HEMT, like GN, etc. So all these devices play a key role in developing this power electronic converters. And coming to the different converter structures, so for as already mentioned, the solar PV, we need to convert DC to DC. Sometimes this DC to be converted into AC if the load is of AC. And similarly, wind turbines, AC is to be converted into DC, and that also is to be converted back to AC for if the appliances are AC. If you are using a battery storage system, and that should be bidirectional DC to DC converter. Why this is bidirectional? Because battery has to be supply the power to the load, and similarly this has to be battery has to be stored. This power need to be supplied to the battery for charging purpose. So the flow is bidirectional. That's why the bidirectional DC to DC converters. Then we have multiple converter types like in microgrid. And in all these power electronic converters, the only concept behind this just on and offing of a switch. So what happens when the switch is on and what happens when the switch is off? Like first we will talk. So when we are starting the power electronics course and we will start with a single switch. Like if we are connecting, we are just giving a source and you have a load in between that. Sorry. In between that, you are having a switch, and that switch is a power electronic switch. So normally in the signal electronics, like normal electronics, it is actually dealing with very low power, and also it is operating in the, like, it is an active region. And when we are talking about a switch, a power electronic or a semiconductor switch, it is having active cutoff and saturation region. So that signal electronics deals in the active region, that is amplification and all. If you're talking about transistor, but if the transistor is used in power electronics, it operates. It will not operate in the active mode, active region. It operate in the either in the cutoff or in the saturation mode. So that we are simply telling it is very simple. It will give what is the waveform and what is the equation when the switch is on, and what is the waveform or equation when the switch is off. This is only the concept we are dealing with all these converters. We will start with the one switch, then we'll connect more switches depending upon the complexity of the circuit or the load requirement. So, and when you're talking about, you were always heard about, if you are in different branches, you may always have maybe duty ratio of the switch. When the switch is turning on, that time is we'll call as T on, and the one period when the switch turn on and off, one period, we will take it as a time period T. So duty cycle is simply T on by T. So by controlling the turn on time of that switch, we can, by giving the gate pulses, if it is IGBT, MOSFET, or thyristors, and by giving the gate pulse, we'll be able to turn on the switch. So the turn on period we can control. So duty ratio control means you can control the switching turn on and turn off, or turn on, the switch can be controlled, and thus you'll be able to control the duty ratio. So when you're talking about all the controls of the DC converters and all, DC to DC converters and all, we always tell that by adjusting the duty ratio, we are able to control the output voltage or output power, whatever it may be. And that is actually what you are doing. You are simply controlling the on and off time of the switch. And that is the concept behind the switching principles in power electronic converters. And this, we have heard about hard switching and soft switching. Hard switching is actually without considering if there is a voltage current present, we are turning on the switch. That is called hard switching. But soft switching, we will turn on and turn off the switch when the voltage or current is zero. That is called the zero. So what is the advantage of that? Then we will have the switching losses will be very less, because during that time voltage or current is zero. So switching of EMI will be less. But the problem is the implementation is complex compared to the simpler compared to the hard switching. Okay, and then coming to the power quality issue, and what actually the quality of the power we mean, the power quality, and when we are seeing the waveform, if our load, like our fan load or motor load or light load, this load is having a specification, and that load require a pure sine wave. If it is an AC load, and that load require a pure sine wave. If the sine wave is pure, we'll call it as it is a best quality wave. It is best quality power. If the voltage and current is having a pure sinusoidal, whenever it is deviating from that sinusoidal waveform, we will tell this is having a harmonics. This is having harmonic. This is having issues. So, and if we are introducing power electronics equipment, converters, switches, power electronic converters into the gate into the circuit, what happens? Definitely there will be deviation from the pure sine wave. So we are injecting harmonics into the system. So if we are injecting, it is our duty to reduce the harmonics. So what we will do, we cannot move with the usage of this power electronic converters. So what we will do, we will use harmonic filters. We need to filter it and reduce the harmonics to the level specified by the standards. Okay. And then we'll see the different control techniques. Then the switching already said that it should be usually all the converters are having higher efficiency, more than 90%. Generally, DC to DC converter is having 90 to 98%. Inverter, bin converter, battery converter, all this efficiency are mentioned here. The AC efficiency is one of the very important factor because we know that the already availability of this energy is limited. We are taking from the renewable energy sources, and that has to be efficiently utilized. For that, like this is a figure which shows the losses, switching losses and conduction losses. See, during the switching, it is having this much voltage and this much current. So naturally, the switching loss will be high. So, and that by reducing the switching loss, we'll be able to improve the efficiency. Now we'll see DC to DC converters for renewable energy applications. DC converters for renewable and this the different converters are buck converter, buck boost converter, cuck or choke converter, septic converter, high gain converter. Different converters are there. I will mention few and review how the operation is happening. And based on that, you can, if you are interested, you can look more into the this converter side. You can do research in this fields. But a lot of research is available in different converters, their topology, circuits, control, and all. I'll just give you how the circuits are operating. And this buck converter, actually, it is a step down converter. If we have in output voltages less than the input voltage, so that's why it is called a buck converter or step down converter. The circuit is very simple. As I already said, we are having a switch. You are having a switch, and that is marked as SW. And we will turn on the switch by giving the gate pulses. You'll turn on the switch. Then the DC power is fed, and it is moved to the inductor, and then given to the load. More, and so you will get an output voltage V in VO is equal to VA. What happens when the switch is off? Already in the previous slide, the inductor stores energy, and when the switch SW is in the off state, the stored energy in the inductor is given to the load through this diode. So this is very simple circuit. Sorry. So based on that, we have drawn the different waveforms, voltage across this inductor, then the current inductor is charging, then discharging. Similarly, the other waveforms are also shown, so that here we will get the voltage VO is equal to TB in. So D, we know that T on by T. So this is always less than D is always less than 1. So VO is always less than the input voltage. That's the name step down link buck converter. What is boost converter? Boost converter, definitely it is boosting the output voltage. And this what is these requirements, and this has to be connected. If we are talking about the solar plant, the voltage generated from a plant may not be as required by the load. So you need to boost the voltage. So we need to use the boost converter. And here also the operation is similar. Like when you are turning on the switch, supply is given through the inductor, and inductor is charged, energy is stored in the inductor. It is moving like this. And when we are turning off the switch, the stored inductor is flowing through the diode and it is given to the load. And this is the operation. As I already said, this is very, our electronics is very simple. The converters are very simple. We are only dealing with the on and off of the switches. If you are, we understood one concept, and that will be given to multiple, complex circuitries. And here we can see that we are getting a voltage VO is equal to V in by 1 minus D. So D is maximum value of D is 1. If it is 1, it will go to infinity. So, uh, uh, so output voltage V in by denominator is less than 1. So always your output voltage is higher than the input voltage. So you will get a boost converter. And then buck boost converter, it's actually giving both step up and step down conversion and DC to DC converter. And see, this is the combination of the switch. And here it will give both buck mode and in case of a solar power plant, sometimes we need to increase the voltage in the morning session will be getting very less radiation, so voltage will be very less. So you can the switch into the boost mode. So that time D is that and all will be automatically done in the system. D is less than 0.5. In the boost mode, D is greater than 0.5. The equation is like this. So you can, if you put it in the value, you'll get whether it is in the buckboard or boost mode. And here the polarity of the output voltage coming as negative polarity. It is coming like this. See. And then as the this converter or chip converter, different names are pronouncing like this. And this is also operating what is happening when the switch Q1 is on and what is happening when the switch is off. So for the here, the advantage compared to the previous converters, it is having like continuous input current, continuous output current. Because of this two inductors L1 and L2, always our output and input is running with continuous current. So the ripple will be very less in compared to the previous converters. And then coming to the septic converter, in the previous case, we'll be getting a voltage which is the polarity is negative, and this septic converter is giving almost all the similar performance of the previous converter with a positive polarity voltage. And flyback converter. And in the previous case, different converters are there. I am mentioning few only. Flyback converter difference is that it is having an isolation. We can see a transformer here. So there is an isolation. When the switch is on, what is happening? The power supply is flowing through the primary to the like this when the switch is on. When the switch is off, what is happening as the stored energy in this secondary is given to the load. So there is an isolation between the circuit. And this is a high gain DC to DC converter. So there are different high gain converters. So this is an example interleaved boost converter in which in the solar applications and all, this high gain because the efficiency is important. So high gain is important. So using this high gain DC to DC converters improves the overall efficiency of the converter. Here also the operation is very simple. When the Q1, when the switch is on, current flows through L1 and then through the switch. And when Q2 is on, current flows from input L2 and through the switch Q2. When this is off, when Q1 is off, the stored energy is given to the load. Similarly, when the Q2 is off, the stored energy is given to the load. So this explanation is very simple. In this way, this is operating high gain DC to DC converter. Then we'll move on to the inverters. So if we are using a DC to DC converter means the unregulated DC power is converted into a regulated DC power so that the DC load gets its required power. And similarly, in the case of as shown in this figure, if we are taking power to our house or to the utility meeting, our KCB, we are supplying, we are having in our house, we have a solar plant, and the power, we have excess power. If our plant is at grid connected power, KCB connected power, then this has to be given to we know that the power generated from the solar power plant is DC, and that is to be converted into AC. So we need to use an inverter here, and this inverter DC into AC, and that has to be given to the grid. This also we cannot give directly to the grid, and there also synchronization and all these things will be taken care of in the inverter itself. And this is the concept of inverter. DC power is converted into AC power. And this is a very simple concept. Like this is DC, how DC power, I mean AC power is generated from, and this is our DC battery. And we are connecting 4 switches. This is single phase inverter, 4 switches S1, S2, S3, S4. We can name like this. Anyway, you can name. So DC power, when the switch is S1 and S2, suppose these two are marked S1 and S2, then the supply DC power is moved through the switch, then to the load, then to the back to the source. Okay, back to the source. So we can see the direction of the current is in this direction. This is our load. We have connected the load here. The direction of the current is like this. So I am marking this waveform as positive voltage. This is positive voltage is coming there. Positive voltage because polarity this side plus and this side minus, and the current is flowing in the marked direction, arrow marked direction. Okay. And now I opened these switches S1 and S2 and turned on these two switches are opposite switches are called. I am calling the switches as S3 and S4 like this. So how the current flows, the power flows from this side is plus, and this moves and is through the switch, and the current flows in the opposite direction and moves through this switch and back to the source. So the polarity is this side plus and this side minus. So the voltage is negative. So I will mark the voltage negative here. This sequence repeats so that from a DC you will get a AC, alternating voltage waveform. This is the concept behind the inverter. Okay, and and we are always hearing about PWM inverters, PWM switches, PWM pulses and all. What is actually PWM? Pulse width modulated, pulse width modulation. And if the inverter is operating with pulse width modulation, we'll call it as a PWM inverter. And this PWM inverter is very simple concept. Like it is actually a comparator. It is actually a comparator. This comparator, I have drawn a simple inverter circuit. The inverter circuit that we have shown here. In parallel to this, we have connected diodes. Always when we are the inverters, we will connect anti-parallel diodes for operating in the if it is having an inductive load. So the same inverter circuit is shown here, and in PWM inverter you will be having comparator is there, and into the comparator you are giving a triangular wave and a sine wave. So this triangular wave we will call it as carrier wave, and the sine wave we will call it as control wave. So we are comparing these two waves in the comparator and getting the output pulses. And this comparator, if you want a sinusoidal output waveform, you will give a sinusoidal control wave. And if you want a DC wave, output wave, then you will give your control wave or reference wave. We'll call it as reference wave also. Reference wave as a DC wave. And if you are three-phase sinusoidal waveform, then you will give three sinusoidal waveforms, which are out of phase by 120 degrees as the reference wave. And these are comparing with the same triangular wave. Then you will get your required voltage. That is the concept behind the pulse width modulation PWM inverter. And actually, the PWM inverter works with the principle, like as I already mentioned, it is having a triangular wave, and that is compared with the sine wave. I have, in order to make it clear, I have drawn a part of the sine wave only. So see here, you can see this is comparing means it is giving to the comparator, and this two waves will be compared, and its comparator output, this is the control law for the generation of the pulses. The PWM concept is very simple. You have just a comparator with two waveforms. A carrier wave is actually the triangular wave, and the control wave can be any wave depending on your output requirement. So if we want a sinusoidal waveform, we will give a sinusoidal waveform. So how it is controlling? If your control V sine wave, control wave, I'm calling it as V sine wave because we are giving the sine wave here. V sine is greater than V triangular, we'll get 1. V sine is less than V triangular, we'll get 0. This is very simple concept, and that is only the PWM. So see here, based on this concept, how you're getting the output. See here, V sine greater than V triangular. See this from this point to this point. See here your sine wave is higher than this triangular wave, right? Sine wave. Then you put 1 here, very simple. Then from this point to this point, see your sine wave is less than the triangular wave. Triangular is in the upper part, so less than then you put 0. It's very simple. In this way, you do all the here. See, from this point to this point, you will get 1. This point to this one, you will get 0. This is how the pulses are generated from the PWM. Very simple, right? So this is a complete comparator output with the comparing with this full sine wave. In the previous I have shown this the control load. So in inverter, if it is a single phase inverter, you can generate the pulses by comparing the one sinusoidal waveform so that you will get your VA voltage. And if you are comparing the same triangular with your negative voltage, you will get the VB voltage, VB pulses, voltage pulses. Then what is VAB? VAB voltage is just VA minus VB, just minus VA minus, this is your VA minus this pulse from this. So see here, you will get an arrow pulse and then 0. This to this part, this are 2 are 0. So you will get 0 here. Same voltage, so you will get 0 here. Then, then just taking the difference of these two waveforms, then you will get a voltage like this. And so the fundamental voltage is of this PWM, you will get it is a sinusoidal waveform. Okay. And similarly, if you're talking about three-phase PWM inverter, as I mentioned, and this is actually a square wave inverter, and just to know how the operation is. A three-phase inverter, we have 6 switches, 3 top switches and 3 bottom switches, and that has to be operated in a switches are to be operated in a sequence to get your square wave voltages, pulse voltages like this, and just given the some switching operation like during the mode 1 and this mode, you'll be having switches S1, S6, X2. I'm not describing all this. S1, S6, S2. That means your three-phase inverter switches at a time during from 0 to 60 degree. The switches which are in the on state are switch 1, then switch 6. Sorry, this is the 1, 3, 5, 2, 4, or 6. Name is differently given. Sorry. So this is actually giving how what are the switches to be switches that are on in the one particular period, and based on that you'll be getting different voltages. And if you're talking about three-phase PWM inverters, it is giving see three reference ways or three control ways. Reference sine wave phase A, phase B, phase C, and that is compared with the same triangular wave. Same triangular wave. So as we already mentioned, if we are comparing a triangular wave with the reference A phase, you will, by applying the same control law as we have seen earlier, you will get these pulses, so that you'll be getting a fundamental like this. And similarly, you compare B phase voltage with the same triangular wave, you will get VB pulses. And when you're comparing C waveform, phase C waveform with the same triangular wave, you will get this waveform. And then you can, as we have already mentioned, you if you want VAB, VA minus VB. If you want VBC, VB minus VC. Then if you want VAC, VA minus VC. In this way, VCA, VC minus. In this way, you are able to get all the line voltages, and these are the phase voltages, so that you will get the fundamental PWM three-phase output voltages. And this is how we are generating the PWM pulses. Then the other inverter types are multi-level inverters. And there are different multi-level inverters. As we have already mentioned, if you're using simply a square wave inverter, the square wave is having the maximum irregularity, like maximum harmonics. And for that, we are using any waveform can be converted into different Fourier series, right? So series, right? Like different sine combination of sine. Like that is why we are telling that second harmonics, third harmonics, fourth, fifth, sixth harmonics, different seventh, odd harmonics, even harmonics, etc. So a square waveform is having the maximum distortion, maximum harmonics. So whenever it is reaching to your sinusoidal waveform, it is having less harmonics. So we will try to make our waveform by using multi-level inverters. We'll try to make our waveform more closer to the sinusoidal waveform, and that is why the multi-level inverters are used. Like this is a three-level multi-level circuit setup, just to show how it is operating. Like when switches S4 and S3 are operating, you will get a plus VDC at this output. And when the bottom switches are operating, you will get S1 and S2 are operating, you will get minus VDC. And when the middle switches are operating, you will get 0. So it is having three levels: plus VDC by 2, minus VDC by 2, then 0. So you are having a three-level inverter. And this is how multi-level inverters are formed. For getting, this is a sample waveform for a five-level inverter. See, here you are having one voltage 0, then next V2 level voltage, then V3 level, V4 level, V5. So this is a five-level multi-level inverter. So if it is three level means it is away from the sinusoidal waveform. If it is five level means it is almost, closest to the sinusoidal waveform. If it is 9 level, it is more closer. But when we are increasing the levels, the switching losses will be more. So we need to have a compromise between this, like how much levels, and also complexity, cost, everything is to be considered when dealing with multi-level inverters. And this is just, I am giving the concept for you, how it is operating. And then this the different converters we have seen. Then coming to a solar PV system. Sorry, solar PV system. Uh, See, we have different solar power plants. Like it can be a standalone PV system. In this, we have a PV array, and PV array is generating the voltage, that is a DC voltage, and that has to be controlled by a charge controller. This charge controller is having the converter, DC to DC converter that we have already seen. The converter can be any converter like buck boost, pick any converter depending upon our requirement or the application or the cost, complexity and all. And this will convert into a regulated DC voltage. And this is controller. And this is giving to the battery bank to charge the battery, PV, then control converter, and then charging to the battery. And at the same time, it has to be directly used by the load, so it has to be converted to an inverter. If we have any DC load, after the charge control, you can give directly to the DC load. And if we have in our house, if the load is of AC, we need to convert to an inverter. We need to convert this DC into AC, and so that we have connected to the distribution panel and to the AC loads. And this is completely a standalone system. That means it is not connected to the grid. It is this, that's why we are calling it as a standalone system, or we'll call it as off grid. It is not connected to the grid, off grid system, right? And now we have a grid connected system, and this is connected to the grid. Grid means in our Kerala, it is KCB. KCB lines, and that is our grid utility grid. So we have PV array. Then it is a completely grid connected system. We don't need any battery there. And so PV panel, our plant, which is connected in our rooftop as generating DC power. And this is connected to the grid connected inverter. This is given to the grid connected inverter. Actually, this grid connected inverter is having all the DC to DC converter, MPPT, and the normal inverter. I will explain in the next slide. But the name that most of the companies are given is the inverter, grid connected inverter. And then this DC is converted into AC, and this is given to the distribution panel and then to the grid, or to the, if it is directly used by the load, that excess power is given to the grid. So there is a net metering here. The pricing is like how much energy we given to the grid and how much we taken from the difference is taken, and this is this is used to calculate the our bill, current bill. This is how the grid connected system is. Most of the big systems are grid connected system because the battery bank used for this large system is very, it may require a full room. It may require a full room to store this battery bank. So usually all the bigger systems you will use a grid connected system. But the problem with this grid connected system is that when the supply is turned off, or our PV, our plant will also turned off. Why this is required? That we call it as the anti-islanding is required because in anti-islanding system, so it has to be when the KCB supply is turned off or the grid is turned off, our power plant should be isolated. Why? Because if someone is working in the grid for for maintenance and all, what happens? The power generated from our solar power plant will go to the grid, and it will, I mean, damage, or it may affect the person who is working in the grid. And then, so when we are installing a PV power plant, the inspectorate will check whether all these requirements, like when the supply is turning off, our grid, this is isolating, or what is the injection of power, I mean THD. THD is the level of harmonics that we are measuring, and we have a standard, it should be less than this much percentage. And they will check all these requirements, and after checking only, this will be connected to the yeah, will be allowed to connect to the grid. Otherwise, the problems, there may be problems like this. And next is and the problem with this grid connected system is that when the supply is off, our complete plant is in the shutdown mode. So we won't, even if there is sunlight, we won't get any power to use. So in order to overcome this, we have a hybrid PV system. And for that, we'll be using, it is connecting to the grid, and also not complete power, a small battery bank is connected, so that we can connect this battery bank to the critical loads. Like some critical loads for important loads can be fed from this battery bank, even if the supplies, I mean, even if the KCB or utility grid supply is not available, so that our PV generation can be utilized effectively. And the battery bank capacity can be determined according to our requirements. So how much, I mean, what are the devices to be turned on during the shutdown period, or KCB supply is not available. Based on that, we'll be able to design the battery bank requirement capacity required for that. Okay. So here, similar to the PV array, charge controller, and then bimodal inverter, it can operate distribution panel, DC load, grid connected, all these things. Like, along with this, we have a battery bank also. That is only the difference. So coming to the solar inverter, the company is specifying it a solar inverter. So in the solar inverter itself, it is having our DC to DC converter that we have already seen, like buck converter, boost converter, all this type of converter, any converter. Then we have DC to AC converter that we call it as inverter when we are seeing the basics. Then maximum power point tracking, MPPT. So all these devices are embedded into the solar inverter supplied by the companies when we are installing a solar PV system. Okay. See this DC to DC converter we have already seen. Then this inverter circuits we have already seen. Then just mention what is the MPPT, maximum power point tracking system. And this is actually when we are talking about the PV module. Like any device, like if you are studying the devices like a diode or a transistor, we will start with its VI characteristics, right? And similarly, this PV module, that is PV module, the basic unit is PV cell. That is actually a diode. uh, uh, okay, that is actually, the structure is similar to the diode. So we can see the VI characteristics. There is a VI characteristics, and from that you'll be able to plot the power characteristics, voltage, current, and the power curve. And here we can see that we'll be able to find out, like, voltage and current multiplied, we'll get power. So we'll be able to plot this curve. So we have two curves with the different radiation levels. And here you can see that at this point, at the peak point, you'll be getting the maximum power. This peak point, you'll be getting the maximum power. So if you are able to tap this peak point power, you'll be able to get the maximum power out of the installed power plant. So, and for that, we need to use some circuitry and some programming to get this maximum power. And this is a VI characteristics of plant with different insulation levels. Insulation levels means radiations. And this is, we have the first is having like some morning, you'll be having a very light radiation will be very less. So you'll be having an insulation 200 watts per meter square. And after that, at noon, you'll be having 1,000 watts per meter square insulation, very bright time. So you'll be having higher voltage and current. And see, so all the time we have it, our load is fixed, right? This is our load line. So usually it is operating at this when our VI carrier is crossing this our load curve. This is the operating point. And at 400 watts per meter square, this is the operating point. And 600 watts per meter square, this is the operating point. But we know that our peak point, but the power curve is not shown here. Even then, this is the maximum power point. So if by anyhow, if we can shift this operating point from this to this, you will get maximum power. So how to extract this maximum power? So different and that is called the maximum power point tracking circuits. Maximum power point tracking circuits. And this configuration, and this is actually a transformer less configuration. And here, sorry, time, I'll quickly try to finish inverter configuration. And here, what I am intended to say is that here, this is our boost converter. This is actually a solar plant. Then filter EMC filter is there. Then we have this DC is given to boost converter, and this will boost, and you will get an output DC again. And then we have a PWM bridge inverter that we have already seen, an inverter setup, and that inverter is giving an AC voltage, and that is given to the grid or to the load. Here we have a load AC voltage. So how you will be all these things, data and interface, these are the controllers and measuring and measurement and control part, this right. So here we have maximum MPP regulation. What is actually that? Maximum power point tracking has done, the control law has done in this block. What is this actually doing? It is adjusting the duty ratio. I have already mentioned that by adjusting duty ratio, you will be able to control the output voltage. What is actually this duty ratio? It is the switching, controlling the switching time. We can decide how much time the switch is to be on, what switch is to be turned off, and that is the and how this is controlling. So in order to get the maximum power, this is we have seen the maximum power transfer theorem when the load impedance is equal to the circuit impedance, it will give maximum power, transfer maximum power. The same principle is used here also. So this side, when this side impedance or resistance as impedance is matching with this side, this will give maximum power. So the duty ratio of the switch is adjusted in such a way that both the sides of the impedances are same, and it will fix the duty ratio at that point so that it will extract the maximum power. That's all. And then I'll quickly 760. Wind energy. Similarly, the other system is a wind energy conversion system. Here, see, we have wind turbine, and wind turbine, when wind turbine is running, it is having a shaft, and shaft is also rotating. And to the shaft, we will connect the bearing and all rotor and all the things will be there. And this is connected to a turbine. And when the turbine rotates, it is connected to your shaft is connected to the generator, and the generator moves. When the generator moves, it will generate electricity. And this is an AC electricity. And the generator, and that is the converter. Here we are using a converter. It is converted to DC, and the DC is again converted to, and why this conversion is required, in why we can directly use this DC, right? Then, but it is again, but for the control purpose, we will use DC link, like voltages if you want to control the speed, voltage, we need to control different aspects from the feedback control. We will use a control circuitry, and this has to be given, and then we need to be conversion is to be required. Okay, right. And then this is given to the grid side, and then uh, I mean, grid side we need AC. So it is converted to AC and then given to the transformer and then to the AC side. Okay. And that is the wind energy conversion system. I'm not going, it's already time as the late, so I'm not going into the more details. And then we have battery energy storage system, BESS. We'll call it as nowadays. Generally, always people are always talking about BESS system. And here in our college also we are planning to have a BESS system because diesel generators are also diesel generators are used and it is not environment friendly, and also we need to be in the sustainable way. So large battery banks are used to store the like lithium and or lithium ferrophosphate batteries are used as a storage device instead of this. So here also the battery management system are to be there. There we need to manage like whether batteries to be charged or the how much power is to be taken from the battery, and for that also we need converters. It has to be converted into AC, DC, DC to DC, and all conversions and communications are there, and this has to be controlled like that. Okay. And coming to the microgrid setup, I will finish it within 5 minutes. And coming to the microgrid setup, microgrid means we are combining all the renewable energy sources, and that we smart micro will call. We will use different algorithm, battery energy. I mean, energy management systems, how much power to be given to the, what are the critical loads to be given, or we will do the algorithms and all, and this will be effectively and efficiently controlled, and that is a microgrid system. And then coming to the conclusion, so power electronic converter as a critical part in the renewable energy conversion setup. So the future scope is very vast, like the penetration of renewable energy and EVs and the sustainability as the point of concern for everyone. So the power electronic converters are a crucial part, have a crucial role in this. So we have the research potential in this area is very vast. We can use devices, high performing devices, HMTs and all for the conversion. Then AI powered, AI has to be, AI can be incorporated with this machine learning program, deep learning, all these things are can be done in microgrids or in circuitries like BMS, I mean, battery energy management system and all, and a lot of research potential is there in this system. Okay, thank you.
Thank you, ma'am. Participants, if you have any queries, you can unmute your mic and ask, or you can put it in the chat box.
No questions? And you can mail me also or message if any queries. Okay. But coordinators may be having my mail ID. Okay.
Yes, Miss.
Thank you. Thank you for the patience listening. Thank you.
Thank you, ma'am. Thank you, ma'am, for such an insightful and engaging session. Your valuable expertise, practical insights, and clear explanation have truly enriched our understanding of the topic. We sincerely appreciate the time and effort you have taken to share your knowledge with us. On behalf of the Department of Electrical and Electronics Engineering, I extend a heartfelt gratitude to you. Thank you once again, ma'am, for being with us today. We look forward to interacting with you again in the future. Thank you, ma'am.
Thank you.
Now we can move to our next session. Let me introduce our esteemed speaker for this session, Dr. Sobha Manakkal, professor in the Department of Electrical and Electronics Engineering at Nehru College of Engineering and Research Center, Pabadi, and former vice chair of the IEEE PES Kerala chapter. She had her doctoral studies from NIT Calicut, and the research area includes damping of low-frequency oscillations in power system. She has 4 years of industrial experience and more than 20 years of academic experience. Today, she will be delivering a talk on AI-based FACTS controllers for damping of low-frequency oscillations in power systems, a topic of great relevance to modern power system stability and intelligent control. We are honored to have her with us today. I request all participants to join me in warmly welcoming her. Thank you, ma'am. The session is yours.
Dear participants, the feedback link for the session 1 has been posted in the chat box. Please make sure that everyone have filled. Those who are having only 80% attendance will be provided with the certificates. Thank you.
Hello, am I audible?
Yes, ma'am.
Am I audible?
Yes, ma'am,
Yes,
you're
ma'am.
audible, but there is some echo, ma'am.
Yeah, let me. One minute. Okay, am I audible now?
Yes, ma'am, you're audible.
Yeah. I think I'll move a little away
Ma'am, the
because,
echo is still existing, ma'am.
yeah, echoes because, hello,
Yes, ma'am, we can hear you.
Yes, ma'am.
it's okay now?
Now it's okay, ma'am.
Yeah, I'm moving out from my another issues. Can I do one thing? I will share my presentation to Sharanya. Can you move the slides?
Okay, ma'am.
Or otherwise, if too much of echoing is there, let me just. Hello.
Yes, ma'am.
Yeah, I'm trying. Hello.
Yes, ma'am.
Now I'm audible.
Now it's clear, ma'am.
Yeah, and screen is also visible, I hope.
Yes, ma'am, visible, ma'am.
Okay,
Yes, ma'am.
now it's okay. Okay. So, shall I start the presentation?
Yes, ma'am, you
ma'am.
can start, ma'am.
Okay. So, first of all, let me thank Sharanya for inviting me for this presentation. And let me just congratulate the faculty members who have taken initiative to conduct such a program, especially in this major area in which globally we are all looking for solutions to bring down the global warming level and to improve the sustainability. Everywhere the word sustainability is echoing, and as far as power system field is concerned, this is of much importance. So I'm happy to share some research experience I'm having, and of course my experience with respect to power system stability, and a little bit of renewable energy problems also I will be discussing through my presentation. So the topic is AI based FACS controllers for damping of low frequency oscillations in power system. So we will see what exactly low frequency oscillations are, why we should have so much of concern over low frequency oscillations, and how we can mitigate them in a conventional system using FACS controllers, flexible AC controllers, and perhaps with AI based control methods. And we will just peep into how what more measures we have to take as far as renewable integrated, highly renewable penetrated systems are concerned. So that will be my flow of presentation. So to start with, as everybody knows, power system is a network of electrical components which has to facilitate generation, transmission, distribution, and utilization. And of course, when we are doing this process of generation, transmission, distribution, and utilization, there is one important concern, that is, it has to be stable, it has to be reliable. So these are the two major factors a power engineer has to be looking into, whatever be the mode of system, whether it be a microgrid, whether it be a smart grid, whether it be a renewable grid, it has to be stable and it has to be reliable also, because they are coin same part of the coin, same side of the coin, I should say, because if it is not stable, it is never reliable also. So it has to be ensured. But then we can see that there has been ever increasing surge in the workload, because every time a new gadget is being added to comfort our own life, and there has been an ever increasing rise in the demand for electricity. And this is bringing out a lot of operational responsibilities strain in the energy management system, because managing the energy system is very important, and this is training them So it has become the need of the hour to embrace evolving technologies, basically the AI system. So no system is going to survive without the support of artificial intelligence, because a lot of data is going to come into picture, and you need to have a smart grid where digitalization is required for all this. You need to have the embrace the evolving technologies. So we'll just examine how this is doing a job in the conventional system to start with. So if you're examining the power grid over a century, we know yesterday's power system was Thomas Edison system that was serving just 1 square mile in New York. It was basically a low voltage 110 volt DC system, and it had its own difficulty because DC systems never had the facility to enhance the voltages at that particular time, and transmission which happened in this low voltage could not travel through long distances. So that was a major disadvantage. And as years passed through, that is Tesla came into picture with an AC system. And I think most of you might have heard of war of currents, where there was an open fight between Thomas Edison's DC system and Tesla proposed AC system. And naturally, because of the invention of transformer, which could beautifully enhance the voltage to the required level, which made it possible to transfer energy through long distances faithfully, took its shape, and so AC superseded the DC system. So that was today's power system, which came into existence with a highly complex interconnected system with sharing of resources. As most of you will be knowing, our country is divided into 5 zones: northern zone, southern zone, eastern zone, then 5 important zones, which is there is a possibility of power to flow from northeastern region to southern region through something called a synchronous grid. And because of the connectivity of the southern grid also to the total system, now the entire nation is having just one synchronous grid, one nation, one grid, one frequency. So that is today's power system. But then tomorrow's power system, we are looking for threefold increase in the power, adding IT smarts to bring digital intelligence throughout the power system, which you are calling it as an electric grid. This is going to be the tomorrow's power system. So now we are in the transitory stage from today's power system to tomorrow's power system. And this is in the view of having more and more renewable penetration. So this is where exactly we are standing. And in this context only, we are going to discuss over the stability issues, how to mitigate them, how we can use AI for that under this context. So when we are talking about interconnected power system, they are naturally complex. They travel through longer distances. It can be overhead lines, underground lines, through seas, across countries, and it involves transfer of bulk amount of power. There need to be increased utilization of existing transmission corridors. That means the redundancy is going to come down. All these are going to make the system more complex. And so there has been an increasing concern over power system stability. So at this point of time, let us examine what power system stability means. So here, it is the ability of an electrical grid to maintain synchronism, maintain voltage level at various buses, and maintain a nominal frequency under 2 conditions: under normal operating condition, and also its ability to come back to this particular equilibrium condition after a disturbance. Disturbance can be different types. It can be a fault, sudden removal of a load, sudden addition of a load, then sudden tripping of a generator. All this can be different scenarios under which the system is likely to use its stability. That means the synchronism may be lost, voltages of various buses may come down the particular value, there may be the deviation in frequency beyond the permitted range. Then we can say that the power system is not stable. But if a system is stable, it has the capability to regain synchronism, acceptable voltage level, frequency level within the limits. when it is subjected to some particular disturbance, also under normal. So two things are important. It has to be stable under normal operating conditions. It should come back to the normal condition after a disturbance, for which three parameters need to be maintained. One is it should maintain synchronism, voltage level, as well as frequency. So these are the three performance parameters of a power system, which has to be continuously monitored by an energy engineer. For which, if you wanted to check whether a system is in synchronism even after a disturbance, we should see whether it is stable, rotor angle stability has been maintained. That is deviations of a rotor angle with respect to time, and we have to examine whether it is stable when it is being subjected to a particular disturbance, which you are calling it as a rotor angle stability. Likewise, the voltage deviation with respect to time when it is being subjected to a disturbance. Voltage stability, it is the ability of power system to maintain acceptable voltages at all buses, for which we have to ensure that voltage stability is there. Similarly, frequency stability. Frequency stability, it is the ability of the system to maintain steady frequency that is within the particular range, following a severe imbalance between generation and load. Real power generation, load requirement. If the generation is more than the load, the frequency will go higher than the limits. And if it is lesser, it will come down also. But then only certain very stringent limit is provided for the frequency, because if it is deviating below and above the required range, the total synchronism is affected. All the clocks will be affected. There are a lot of electrical equipments which is functioning on the frequency spectrum. So it is not permitted. So frequency stability is also very important. So these are the three stability issues which is often addressed in order to ensure that power system is stable, that is synchronism is maintained, voltages are correct, and frequency is within the limits. So under this, we can have a stability classification tree as well as power system stability is concerned. That is rotor angle response, which ensures that the system synchronism is maintained. Voltage response, which ensure that voltages at all buses are maintained. Frequency response, which ensures that the frequency is also within the limits when subjected to a particular disturbance. So let us see what are the type of disturbances. That is, you can have two types of disturbances. That is, I will be mostly discussing on the rotor angle response, even though there can be voltage response and there can be frequency response. And we should remember that power system stability means if there is a deviation in the rotor angle response or the rotor angle is going beyond the limits, naturally the voltage response will also be poor, frequency will also deviate, the entire system will collapse. But if you wanted to address the stability issue, we are examining this, whether it is rotor angle problem or whether voltage is that is reactive power problem is there, or real power problem is there, or rotor angle deviation due to the absence of synchronizing torque is there. This is examined and you are addressing the problem. But these are not totally independent. These are all dependent with respect to each other. Any type of stability issue will affect the other stability also. But from the analysis point of view or the design point of view, you are perhaps concentrating on one type of response. And in this particular today's discussion, I will be going in this particular channel, that is rotor angle response, when it can be subjected to different types of disturbances. One class of disturbance is called a small signal disturbance or small signal response. Response is the response of the system when it is being subjected to a small disturbance. Similarly, transient disturbance, that is when the system is being subjected to a heavy disturbance, whether rotor angle response is within the limits or the rotor angle deviations are within the limits. That is being examined. Now, within the small signal response, again, you can have two types of responses. One is called a non-oscillatory response. There are no oscillations. The system will simply go out of synchronism without an oscillatory mode. Whereas oscillatory response, you have different types of oscillations. And the oscillations can be building oscillations, it can be damped oscillations, it can be sustained oscillations. That is the oscillatory response. That is when the system is being subjected to a small type of disturbance. You can have two type of responses, non-oscillatory and oscillatory. Even in oscillatory response, you can have different modes. One is called a local mode, one is called an inter-area mode, one is called a control mode, and one is called a torsional mode. Actually, control mode is because of the lack of damping effects provided by the various control equipments or control methods which is being employed in the power system. Similarly, torsional modes happens in the mechanical part of the system. The turbine, the shaft, etc. will be having modes of oscillations. That is a mechanical oscillations, and this is the control oscillations. Whereas these two types of oscillations are actually something to be addressed by controlling the damping part of the system. And in this, in my study or in today's presentation, we will look into these two types of oscillations and how it can be addressed. Thus, we will be looking into the rotor angle response when it is being subjected to a small disturbance and when it is having an oscillatory response in these two modes of oscillation. Various studies are there with respect to control modes, torsional modes, frequency response. These are different areas in which a lot of research work is happening. And as I told you initially, it doesn't mean that when you are designing a controller to address the local modes, you should also check for inter-area modes, control modes, transient response, voltage response. Everything has to be examined. Then only we can say that the power system is stable, because power system stability has to ensure that the system falls in synchronism, voltages of all buses are okay, and frequency is also within the limit. But for the analysis part of it, or rather design part of it, will be moving in one particular channel. So if you talk about small signal disturbance, it is the ability of the power system to maintain synchronism under small disturbances. So what are the small disturbances? One is small and random variations in load. We know that whenever a power system, every time, at every moment of time, there will be small and random variations in the load, because load is not within the control of the generation part. That is, every time the load will keep on changing, and this will result in small and random variations. Similarly, minor adjustments in the generation. We know that we are having an automatic generation control. So whenever there is a change in the load, the generator governor will change. So minor adjustments in the generator will happen. Similarly, whenever there are changes in the voltages, small changes in the machine excitation will also change. So these are the three probable areas or reasons why you are having, or where there is a need to examine the response of the system under normal conditions. And we can say that this is not a severe condition where the system is having a fault. This is a normal condition. So we can say that this oscillatory response analysis is very much required, because this happens to be an inherent part of the power system. You can never have a power system without these variations. It will always happen. You can avoid possibly a major fault, but this is something which is an integral part of the system. So we can say that the oscillatory response or small signal analysis is an integral or inherent part of the power system performance. So one advantage is, because of this disturbances are quite small, it can be linearized with respect to the operating point. We know that we in control system, suppose you are having a very severe disturbance, it is a non-linear in nature, whereas small disturbances we can linearize with respect to the operating point. So a little bit about the electrical power. Whenever an electrical power system is perturbation means small change. Change in electrical torque of the synchronous machine will happen. This is the basics. So change in electrical torque, it is having two components which are orthogonal, which are mutually shifted with respect to each other by 90 degree. One component is in phase with the synchronizing torque. That is deviation delta. This is the deviation in the rotor angle. Or we can say that synchronizing torque component is in phase with the rotor angle deviation. Similarly, there is another component, damping torque component, which is shifted with respect to this component by 90 degree. It is in phase with the rotor velocity changes. So two components are there as far as the electrical torque of a synchronous machine is concerned. And this happens whenever a system is disturbed or small disturbances. As I already told, small disturbances can be small changes in the load, small changes in the excitation system, small changes in the generation. So this is actually actually, if there is a lack of synchronizing torque, that is synchronizing torque component is that particular component which is in phase with delta delta. If there is a lack of synchronizing torque component, system becomes unstable and the response is non-oscillatory, a periodic drift in the rotor angle. We have seen there are two types, non-oscillatory as well as oscillatory. When synchronizing torque is absent, response becomes non-oscillatory and the system will become unstable. Similarly, if there is a lack of damping torque in the system, you can have, because system again becomes unstable, but the response will be oscillatory, increasing rotor oscillations. So if you talk about small signal stability, you have to examine whether the response is unstable because of a non-oscillatory response or whether it is an oscillatory response. And usually, when a system is working with automatic voltage regulator, there will be enough synchronizing torque in the system and there will be some lack of damping torque. This will be impaired, and modern power systems always work with AVR, that is automatic voltage, fast acting automatic voltage regulator. So as a result, there is always a threat to the damping torque component. That means the system inherently has small changes in the system. When it is working with automatic voltage, fast acting automatic voltage regulators, the system is likely to have increasing rotor oscillations. So this is where exactly a lot of techniques are involved. We always wanted the damping torque component to be large enough so that the system is not going to lose stability under normal operating conditions. Remember, normal operating condition, you always have a small signal stability issues. So you have to address that. How we can address that? So we are going to examine the oscillatory response with constant field voltage. Constant field voltage means there is no AVR. If there is no AVR, the system is likely to have a negative synchronizing torque. See, this is negative and damping torque is positive because there is no AVR involved. That is, the field is kept constant. Under that condition, this is the total electrical delta TE, which is the summation of delta TD and delta TS. However, TS is minus over here. So the system is going to drift like this. This is called a non-oscillatory instability. Steady increase in the rotor angle, delta delta with respect to time. Steady increase in the rotor angle due to lack of sufficient synchronizing torque. This happens mostly when there is no AVR and the system is carrying a lot of power flow is happening and the system is connected to a weak grid, that is short circuit ratio is very small. Under those conditions, there is always a threat for the synchronizing torque and the system may go unstable without any oscillations or without any oscillatory mode. But fortunately, mostly all systems are now working with automatic voltage regulators. So there is no much threat to this type of non-oscillatory instability issues. But more frequently, we are having oscillatory instability. That is, the system is working with the excitation control. So here, damping torque is negative and synchronizing torque is positive. So in that case, steady increase in the rotor angle due to lack of sufficient damping torque. TD is negative over here. So system is having a growing oscillations and we can say that system is unstable. Now here, if you are having enough damping torque, there are different methods by which the damping torque can be improved. And in that particular case, your synchronizing torque is positive. It is working with an AVR and damping torque is positive because you are doing a lot of techniques to improve the inherent damping of the system by examining the various modes of oscillations and trying to improve by adding some compensators to the system. System will have sufficient synchronizing torque, system will have sufficient damping torque, then your system becomes stable. even if it is being subjected to small deviations in load, small deviations in excitation voltage, or small deviations in generator frequency, etc., the system will become stable, and you can say that you have a system stable. So this is what is expected with respect to a system. With respect to rotor angle stability of the system, you have to make sure that there is enough damping torque with the system. So that means you are going to examine the oscillatory response of the system, or which you are calling as a low frequency oscillations. So that is low frequency oscillations in power system due to lesser damping torque. So you can have two modes of oscillation. One is called a local mode. That is, oscillations are localized in small part of the power system involving lesser number of machines. That is the frequency range. That is why you are calling it as a low frequency. It is only from 0.7 to 2 hertz. You are calling it as a local mode of oscillations. And there can be inter-area modes of oscillations. That is, the oscillations are felt in wider part of the power system. It involves more number of machines. The range is 0.1 to 1 hertz. That is, Kerala grid can oscillate with respect to the Tamil Nadu grid. Even though both are expected to operate at 50 hertz, there could be some oscillations, the oscillatory behavior, and this can result in some modes in this particular range. Then we can say that there is a inter-area oscillations with respect to these two systems. That is, one Kerala grid as well as the Tamil Nadu grid. So that means more machines are involved, participation from more number of machines, and oscillations will be felt in wider part of the power system. So this is the different modes of, that is local modes and inter-area modes of oscillations. Now, as I told you, why this arise whenever the power system is perturbed, that is, this is inherently happening, you cannot control that. Similarly, it is observed in all power system parameters, that is all voltage, frequency, real power, reactive power, all this will have a this low range frequency when all the time. But usually it is an inevitable characteristic of the power system. Why? Because there cannot be a situation where there is no perturbation at all in the system. This is continuously happening in the system. So it is an inevitable characteristic of the power system. But you have to make sure that there is enough damping torque so that the system can sustain this. So they are acceptable as long as they decay. That means only solution is you should have enough damping torque in the system. So oscillatory instability is the lack of damping torque. So why? Because of the influence of fast acting exciters. That is why you are putting fast acting exciters, because you wanted the voltage to be controlled. That is, you don't want the voltage to drift. You want to ensure the voltage stability. That's what I told you. One type of measure which we are introducing in the system to improve the stability will affect another system. They are not mutually independent. So fast acting exciters will improve the voltage stability at the cost of introducing oscillatory instability. Long transmission lines carrying bulk power, always interconnection, always a threat to the stability. All stability issues are more emphasized or more pronounced for long transmission lines, transmission interconnections. Again, especially weak interconnections. High speed fault clearing. High speed fault clearing means transient, a sudden disturbance, it is required. You have to clear that very fast. But if you are doing that, it will affect the damping of the system. So all these are the situations under which there is a lack of damping torque, and it may result in oscillatory instability. So that means growing low frequency oscillations. So what is the effect? Effect can be cascading disturbances. That is one whether it be a local mode or an inter-area mode, more machines get involved. This, because it is arising in nature, it can even lead to a total loss of synchronism, system collapse, blackout. So the only thing is, if you wanted to ensure that it is not moving to this particular situation where you are encountering with the blackout, you have to ensure that system is having enough damping torque. So what is the method? What you are doing traditionally is adding power system stabilizers. Power system stabilizers means you are simply adding damping torque to the system. It is acting to the machine excitation system and it is a proven technology for damping of local modes. So this normally all systems are provided with PSS. So there will be enough damping torque in a total power system. There is no threat to the small disturbances which is happening, or the oscillations are damped out as soon as they are formed. So the system is stable. But for inter-area oscillations, this may not always be sufficient. You will have to have more important methods. And similarly, even in I'll be coming to that, even in renewable rich systems where a lot of renewable penetration is there, again the conventional power system stabilizers will not work due to various reasons. I will be briefly touching those points. So this is where we have to have emergence of power electronics technology. So to address the inter-area oscillations, to address the issues of having a renewable penetration into the system, if you wanted to add more of damping torque to the system, you have to have more technology, or you have to depend on power electronic technology. I think right now we had a session on power electronic basics, same thing. Technology is all the same. When you are applying it to the power system, you are calling it as a FACS, that is flexible AC transmission system. This was introduced by Dr. Naren Hingorani in 1990, and this is the IEEE definition for FACS, alternating current transmission system, incorporating power electronic based and other static controllers to enhance controllability and increase the power transfer capability. So this is the definition. What exactly it is doing? Suppose you are taking a conventional system. You have a synchronous machine over here. You have a load, two transmission lines which is being connected to a load. Now, the natural sequence in which the power is going to flow from this machine to this load depends on the impedance offered by this line. Similarly, to this particular load, it is controlled by the impedance of this particular line. So that means load sharing is entirely governed by the line impedance. You can by no means have more power flow through this because the line impedance is rigid. You cannot add length to the line or cannot cut off particular line. It is all rigid. But so you can say that the power flow in a conventional power system is inflexible. But if you are having a FACS device over here, what happens is it is possible for you to increase the impedance over here. That means more power will flow through this. You can reduce the impedance over here. You can transverse more power through this. So that means power flow can be electronically adjusted by adjusting the firing angle. This you are doing by adjusting the firing angle. So you can see that the power system has become now flexible. So that is advantage of FACS technology. Now there are various, group 1 devices, the majority of different types of FACS devices. So I'll be just going through only very briefly through this because it's available in most of the textbooks, and I don't know, most of you might have come across also. One is STATCOM, one is SSC, and a combination of that is UPFC. That is, you are having consider a single machine infinite bus system. This is the sending end voltage. This is the receiving end voltage, and it is being the power is flowing from this end to this end to the transmission line, which is having a impedance of XL. So the power flow is governed by this particular equation. Vs into Vr divided by the transmission line impedance into sine sending end voltage minus receiving end voltage. So suppose you wanted to control the power flow, you can control any of these parameters. So starting with the STATCOM is going to control, it is a shunt connected VSC, regulates the bus voltage. It is going to control the voltage. It is capable of changing this particular voltage. Thereby the power flow can be controlled. Similarly, you are having a series connected. See, this is shunt connected where you are having a current flowing through this by varying the firing angle of this particular device. You can vary the current through this whereby the impedance will also change. So that is a way in which you are varying the voltage at this particular point, at this point of common coupling. Similarly, this is a shunt connected device where again you can control by changing the firing angle, you can control this particular current. That means this ratio will change, or we can control this particular parameter. So using this technology, you can control this voltage. Using this technology, you can control this particular impedance. So SSC, like series connected voltage source converter, which emulates the reactance. This is again, all these are voltage source converters. These are group 2 devices, which is capable of doing reactive compensation. A lot of advantages are there. And finally, if you're having something called a unified power flow controller, the advantage is you can control all of these parameters. That is, UPFC it is a combination of shunt and series. You are having a shunt converter over here. You're having a series converter over here. With using this technology, that is, this can do its own reactive compensation. This can do its own reactive compensation, and real power can also be. If you are taking some real power from here, it can flow through the DC link and can be compensated by taking from, because the real power this cannot generate. So whatever real power compensation is done, it is compensated by the other device. So it is a technology. So shunt and series connected VSC. Using this, it is possible to control voltage, impedance, and even this particular angle. So that is the beauty of a unified power flow controller. Now, this was again proposed by Geigy in 1991, and it can simultaneously, that is at the same time or selectively, control all the parameters affecting the power flow in transmission line: voltage, impedance, phase angle. It is called a unique capability, and because of this capability, it can independently control real and reactive power flow in the line. So that is a UPFC, Unified Power Flow Controller. And in this particular discussion, we can discuss a little about UPFC and how an AI-based UPFC can improve the low frequency can damp the low frequency oscillations in a power system. So now AI-based FACS controllers for damping of low frequency oscillations in power system. That is a topic which I want, after this introductory session, I wanted to take you to this. And we know all the advantages of an artificial intelligence-based FACS controllers. They are adaptive, it is robust, real-time damping of oscillations by learning the system behavior and adjusting the control actions accordingly. That is the advantage of having an AI-based FACS controllers. And artificial intelligence, it is an umbrella term describing the software systems which is able to perform tasks that traditionally require human intervention. So it is able to interact with the environment, analyze it using predetermined rules, and making decisions based on the results. So if you can somehow have artificial intelligence method for FACS controllers, you can do a good job. So these are the various classifications. I think we will not go deep into it. These are the different types of classifications. Now, you can combine this with the traditional mathematical approaches so that it is proven instrumental in addressing various challenges. One is actually the low frequency oscillation damping. So state estimation, optimal power flow, wherever you require vast amount of data to be interpreted, you can always go for AI. So AI is having a lot of numerous applications in the field of power system. So those young engineers who wanted to do research in power system definitely should have some good knowledge of various AI techniques because that is required for finding the solutions. As I told you, more and more data is to be encountered with, and you wanted to have a new technology embracing the power system, so that because we are moving to a digital smart grid and all that. So yes. This is again PID control, automatic generation control. All this conventional systems will not adapt to the real-time changes, whereas AI systems, which includes deep learning, reinforcement learning, all this, it will adapt to the real-time changes. Load shedding, frequency response, all this are AI is finding applications in improved methodology for finalizing how the load has to be shed, what is going to be the frequency response. So it is going to be predictive analysis, all this can be done. Now, traditional is always having a fixed rule and setting. It is not optimal under varying conditions. AI can have changing conditions, that is adjusting to the changing system conditions. So that is the advantage. Again, another important area in which AI can contribute is managing the uncertainty. We know that power system, lot of uncertainty is there. As I told you, even the load is not within the control. They can have different disturbances. You can have different load patterns. You cannot predict, and more or less, because now we are going to depend on those renewable systems, which is totally unpredictable, which is totally stochastic in nature. You cannot predict what is happening. So the generation pattern is also going to be totally uncertain. So that means the need to have AI techniques for managing a power grid is becoming more and more pronounced. So it can model all this and more robustly than a traditional system. So again, the advantage of all these are the advantages of using the need for AI in power system over the traditional techniques. Overall stability and the reliability. So AI monitoring, better control. So real-time data can be analyzed using AI, and overall stability and the reliability of the power system. I think we started the discussion with an improved stability and reliability, which are the two important keys for a good power grid. So these are the various techniques: artificial neural networks, fuzzy logic, evolutionary methods. These are the various techniques which are used to address any problem. But here we are talking about the power system. This is applicable also for power system solutions. Now, AI system is artificial neural networks. This is the typical structure. You have an input layer, you have an output layer, and a lot of learning is happening over here through mathematical formulas, and then you are giving an input and you have an output. By learning, it will learn the pattern in which the input and output are related. So that is the advantage. So feed forward is there, recurrent is there. All these are the architecture of a neural network. Similarly, you are having another technique called fuzzy logic. Fuzzy logic is this is the traditional system, and you have lesser steps. Using fuzzy logic, you can understand the physical system, design the controller using fuzzy rules, simulate, debug, and implement the design. Very easy steps. Whereas if you are going for a conventional system, understand the system, develop a linear model, determine a simplified controller, develop an algorithm. Lot of steps are compromised over here if you are going for a fuzzy logic, because fuzzy logic is excellent on dealing with uncertainty and imprecision. Now, what I'm trying to explain is you can have a combination of AND as well as fuzzy logic. All these are AI techniques. Advantage of AND is that it is learning from large data set to identify pattern. So based on the neurons and mathematical functions. So, and similarly, if you talk about fuzzy logic, it focuses on reasoning with uncertainty and imprecision. It is good in dealing with uncertainty and imprecision. You can have fuzzy rules. If something is like this, then you can have, that is not like 1-0, not like binary. You can have something in between also. So it's a very excellent, depending on the fuzzy membership function you are taking, you can have a very smooth transition from yes to no using a fuzzy logic, because that technique is excellent for uncertainty and imprecision. So we can say that fuzzy logic can handle uncertainty and can learn from complex pattern. All these are intelligent techniques. Combining both, you can have improved accuracy, robustness, real-time decision making. So this is a hybrid method, which is called a combination of fuzzy logic and neural networks. You can call it as ANFIS. So AI based means ANFIS, that is, it is a hybrid model in which you are clubbing both. You are actually designing a system with a fuzzy logic and then training using a neural network. So I can just present a small case study, which is based on my research work, AI based fact solution. Again, the problem is, as I told you initially, addressing the low frequency oscillations in a conventional power system. So this is the problem addressed, and what we are doing is design of a facts-based supplementary controller. We have discussed the various facts-based controllers. STATCOM is there, SSSC is there, UPFC is there, and we have also seen that UPFC is excellent because it can do real power compensation, reactive power compensation simultaneously and independently, and you can have adaptive neuro-fuzzy inference system. That is, it is a combination of fuzzy logic and neural networks, and it is adaptive in nature, or you can say that it is an AI-based facts controller. So design of this, a small brief look into it. This is the approach adopted. So here, before going ahead with any sort of analysis or any sort of design, you wanted to model the power system. So modeling the power system, the typical models are there. This is the Heffron-Phillips model, which is very frequently used for power system studies. It is modified with fax devices. This is also available in the literature. Heffron-Phillips model modified with fax devices, and combined series shunt converter, shunt fax device, that is UPFC. The fax device used over here is a unified power flow controller. The model chosen is Heffron-Phillips model, which is modified with fax devices. So this is the power system model chosen, and this is the fax device chosen. Now, this modified Heffron's model, because any model we are choosing, lot of approximations are there. And you try to make sure that the approximations which is existing in the model you have chosen is not going to impair with your requirement. Now, our requirement here is to study the low frequency oscillations. So the approximation should not affect that. One is effect of damper winding of synchronous machine is ignored. It can be easily ignored because this is rather slow with respect to this effects are rather slow with respect to our interest of study. Similarly, voltage and current responses of armature winding of synchronous machine is described by algebraic equations, not dynamic equations. There also the time frame, or rather the responses, the time response of this particular changes is rather slow with respect to our time frame. Field winding, however, is described by differential equations. Those variations we have to take into consideration. Torque equations are included. Torque differential equations are included. Those changes have to be taken into consideration. Exciting systems by differential equation. Dynamic modeling of fax devices. So this is a snapshot of the approximations done and differential, that is dynamic changes, which is considered in the modified Heffron-Phillips model involving a fax device, which is available in the literature. So this is the model of the system under consideration. This is a single machine infinite bus system. You have the UPFC control over here, and UPFC is having 4 control parameters. One is modulating index of the shunt converter, phase angle of the shunt converter, modulating index of the series converter, modulate phase angle of the series converter. Any of these parameters can be controlled using a typical technology, so that these output of the output of this fax device is going to change, and which is going to, and your requirement is again, you have to find out which are the oscillatory modes which is having lesser damping, and that has to be addressed. So this will give a better picture. That is, you have the power system, you have the fax member, and you are taking the feedback from the system, that is delta omega, which is actually the derivative of the rotor angle deviations. So actually this can give you a clear picture, or controlling this parameter, bringing down this changes to the minimum. You can bring down the delta variations also to a minimum. That is actually the sign of what do you say, rotor angle response or oscillatory response. So delta omega is taken over here, and it is given to the ANFIS structure. ANFIS structure is a fussification module, rule-based inference. Then this is a defussification module, and it is embedded to a neural network. So this is totally an ANFIS structure. And output is the delta U. This is the control signal, which is going to the fax member. And here it is a UPFC. So it can control any of the 4 parameters over here, depending on the design, and that can bring about changes in such a way that delta omega is not increasing, or not delta is also not going to increase with respect to time. That is, your low frequency oscillations are damped. Now this is the design aspect of it. Steps for neurofuzzy: selection of initial fuzzy inference, selection of ANFIS architecture, ANFIS training. All this lot of opportunities are there. So to sit and examine which is going to be better for that, you should justify the reason why you have chosen that. Lot of research work is required over this before designing what is the FI structure you are using, what is the ANFIS structure, what is the that is neural network training you are going to give, how many hidden layers, all these are important. Okay. Now here what in my study I have taken this TNK reasoning mechanism, and these are the justification, that is output membership functions are linear or they are constant because low frequency. We know that the disturbance also is in the linear time consuming, defuzzification is not involved, computationally efficient. Then it works well with the linear techniques, it works well with the optimization and adaptive techniques. So this is the mechanism taken for determination of initial fuzzy inference structure. And the different functions, triangular function, trapezoidal function, different functions are there. Generalized Bell membership function has been chosen, different reasons. Everything has its own. So it is a compromise between time or compromise between simplicity, all those things you finalize on something. So here in this particular work, generalized Bell membership function is taken. We can try out with different other options also. And in this particular membership function, there are 3 parameters. So input is actually, as I told you, deviations in the generator angular speed, delta omega, which is actually the time derivative of delta delta. And output to the proposed fuzzy inference is the damping signal, delta U. So this is what you are giving to the fuzzy, to the fax device, whereby you can have control the, you can ensure that delta omega is within the limits. And there is a range for the membership function, which we are keeping it as -1 to 1. All these are the design parameters. Actually, there are 21 premise parameters and 14 consequent parameters. These are all computed. These are the premise parameters. This is the one. This is available in the MATLAB environment if you are using a MATLAB for that. And training. And first training, 4-layer feed-forward network architecture. You can have more layers, you can have lesser layers. It is again a give and take, or rather a compromise between choice. Hybrid learning algorithm is chosen. Here also different rules are there. More advanced rules must be available. This is a little back at the time of my research. And here you're actually, data has to be prepared. Data has to be made. That is output and input. So these are the delta omega, this is the feedback, and this is the input to the fax controller. So this is generated using a constant gain power oscillation damping controller. So you are designing a power oscillation damping control under various operating conditions, different disturbances. You have the data for training your system so that it becomes adaptive. It will learn from the pattern, and when it is given in some other operating condition, because of the intelligent techniques, it will work by itself. So this is the ANFIS structure. Premise parameters, consequent parameters, input vector, output vector. 4 layers are there. And hybrid learning algorithm, because it is combination again of gradient descent method, least square. Gradient method, as I told you, it is a compromise we are making. Gradient method is slow, and that has a tendency to become trapped in local minima. LSE offers high computational complexity. But you are combining this, it becomes less complex, and it becomes faster also. So a trade-off between computational complexity and resulting performance. It is decided to have a combination of this hybrid learning generation of training data. Design constant gain damping controller under various conditions. That is electrical power, reactive power, different, transmission reactance. And PE, that is electrical power. This is assumed to be changing between low to high. This is all per unit. 0.12, this is a low loading. This is a heavy loading. Similarly, with respect to reactive power, minus 0.01 reactive power shortage as well as reactive power positive. Similarly, transmission line impedance. These are the range which has been considered for training your ANFIS. Then for UPFC, repeat the set. Now, with respect to each and every UPFC control signal, this is done. So your delta omega delta U training pairs from constant gain controller is designed under various disturbances that is going to train your ANFIS. System is again equipped with constant gain and proposed controller. Now comes the evaluation. Now you're designing all this, you're training your ANFIS, and you are going to simulate the system with, what do you say, UPFC, SMIB system with UPFC equipped with constant gain and proposed POD. That is, constant gain is having a conventional controller, and the proposed POD is the ANFIS POD. That is, POD is actually power oscillation damping controller. So the system is considered, you have to apply the disturbance. Disturbance is step change. Step change means a small change. 0.05 per unit. This is a small change in the mechanical input at 0.5 second of the simulation. At 0.5 second, you are applying a small change, step change. That is, it is suddenly removed, 0.05 per unit. So this is the disturbance, and you are examining comparing the effect of whether the proposed POD is good or whether the constant gain is good. So that is the evaluation. And you are doing this at nominal operating condition, system loading above and below the normal operating, system reactance above and below. Different operating conditions are considered because we know that operation conditions keep on changing. It can sometimes work at nominal condition. Sometimes it will be above the nominal condition. Sometimes it will work with slow reactance. All this have to be examined. So this is the results which has been obtained. Now this is under UPFC control signal is delta E over here. That is the series controller delta angle, series VSC control angle we are having. And this blue is without a damping controller. System was not having enough damping under the nominal operating condition. Now with constant gain controller and with proposed control, here some reduction in the overshoot has been obtained with the proposed control. So this is done for various conditions. That is another control signal. P is 0.8, Q is different conditions. This is again machine speed deviations with UPFC. So here also we can see that this is having a better performance. Now low system reactance results are again encouraging. Similarly, high system reactance, it is very encouraging. Proposed controller is doing a good job over here. Then with another control signal, it is again tested under various conditions. It is tested. Some results only are put over here, but in most of the cases, it is seen that the proposed controller is having lesser overshoot, the easier damping, low oscillations, and even this was examined under, I have not got the results actually, transient, that is a sudden disturbance also. There also that is the critical clearing angle was found to be better. So this is low system loading everywhere. And this is again comparing the various which control signal is better. Now overshoot was found to be better with respect to delta E. That is, if you're controlling the angle, it was found to be better. So this is the better control signal. You can go ahead with this control signal for better results. But you have to examine this under various conditions, and moreover, this is with the nominal operating conditions. You can do a lot of exercise over here and find out which is the best control signal likewise. So these are some of the results, and these are some of the references which I have taken. And moreover, now this is with respect to a conventional power system, which is not talking about any sort of a renewable penetration. But now the scenario has changed, as I told you. We are now in a situation where we are moving from an integrated or interconnected power system, highly interconnected power system, to a smart grid with a lot of renewables. So renewable penetration, I think previous presentation also had a brief mentioning on this. So we can easily quick. We are standing third globally, as well as the international renewable energy analysis with respect to 2026 data, 2025 December data, and the renewable energy, including large hydro. Hydro is also considered to be a renewable. Including large hydro, it is 282.7 gigawatts. Total installed capacities. So we can say that more or less 50% of the installed capacity comes from renewables. Not non-conventional, because this includes large hydro, which is actually conventional. Solar is 150, followed by wind is 57. This is the statistics which is taken from the MNRE sites. So now, how is it going to, why we are interested in low frequency, or why we are interested mostly in doing a lot of studies on low frequency? There is reduced system inertia. This is because renewable plants are interfaced through power electronic converters. That is essentially there. There is no physical inertia introduced to the system. When we are talking about the conventional system, we are having a synchronous machine, and each and every synchronous machine is going to add to the inertia of the system. So as a whole, a conventional system is having a lot of inertia with that. And inertia is the excellent damping. Whenever a system is having a deviation with respect to the nominal condition, it is absorbed by the system inertia. Whether there is excess power in the system, because of the inertia that changes, that it is an excellent damping system. However, in a renewable system, the structure is different. There is no synchronous machine. You are using power electronic converters, so physical inertia has tremendously come down. Lower inertia leads to faster frequency dynamics, can increase the severity of oscillations following disturbances. So there is an increased threat on oscillatory response of the system because your system inertia has come down because of lot more penetration. We know that 50% penetration is happening. Similarly, reduced damping. Conventional generators inherently provide damping through electromechanical characteristics and power system stabilizers. Power system stabilizers are going to act through the excitation system. That provision is also absent. Replacement of synchronous generator with inverter-based resources will reduce overall system damping because PSS cannot act through the inverter-based resources. There also damping has come down. New oscillatory modes have developed. Converter loops, control loops of wind turbines, solar inverters, HVDC systems, they will interact with each other. So new oscillation modes, we discussed about control modes, torsional modes, local modes, then inter-area modes. Now new modes of oscillations, which is not present in traditional power system, though. So mode of analysis is required, how to address them. And increased inter-area oscillations. Large renewable plants, they are far from the load center, so power has to travel through long distances, so poorly damped inter-area oscillations. So we can say that there is a very imperative threat on low frequency oscillations because of more and more renewable penetration, and there is a need to have more and more serious studies on how to damp these oscillations. New researchers should come up with solutions for this. And similarly, you cannot go without that is conventional systems will be having PSS. Then HVDC definitely has become a part of the system. Fax devices is required, so they will wind turbine controllers, inverter controllers. All this will interact with each other. Poor coordination. This is again another reason which can destabilize the system. Then operating point variability. Renewable generation, as I told you, it is totally stochastic in nature. You cannot predict. It will fluctuate with weather conditions. So it is controller tuning becomes more and more difficult. So weak grid conditions. This is yet another area which has to be stressed upon. High renewable penetration can reduce the short circuit strength. So that means the grid has become weak. Weaker grid, more tendency for losing its synchronous torque as well as a damping torque. So converter driven oscillations, voltage instability can happen. Reduce observability. Traditional monitoring methods will become inadequate. Real-time monitoring becomes more important. All this, you have to have some AI techniques, then only you can address this. So the solution is advanced power system stabilizers, grid forming inverters, virtual synchronous generator, wide area damping controller, fax devices, AI and adaptive control techniques. These are the techniques which are looked upon by researchers so as to address this oscillation mitigation techniques with RE penetration. So this is adaptive and intelligent control. Adaptive neurofuzzy inference system and reinforcement learning are increasingly applied to fax supervisory loops. These AI layers retune, that is POD controller, they retune and the phase lead time constants in real time as the instantaneous renewable penetration level varies. This is not happening with respect to a conventional system, because for a conventional system, you know that there is some AGC control, AVR control, and all those things. But here at the generating side itself, even though the demand has not changed, even though no disturbance has changed, there can be tremendous change in the input side. So that is another threat for which there is no other solution other than moving with adaptive and intelligent control. So again, talking about the benefits of the system, adaptive to changing solar and wind output, effective under weak grid conditions, and long transmission lines, lesser short circuit constants, and then weak grid. That is the outcome. Can coordinate multiple fax devices, can handle non-linearity, small signal stability, reduce the risk of inter-area oscillations. Overall, grid resilience is also improved. So that is the advantage of benefits of AI-based approaches in a renewable dominated grid. So these are the research challenges. Requirement for large training data set. So it should be more, it should be enormous data has to be collected, because the way in which, as I told you, the input side, or rather generation side, is also varying, which is not happening in a conventional system, which is well within our control, because we have excellent governor controls whereby we can actually control the way in which the generation is changing. However, because of the raw material, or rather the wind, how it is going to blow, solar, how it is going to be changing, especially for wind, can change with respect to time, every moment of time. So large training has to be required. Cyber security, that is a common for everything. Real-time computational requirement is there. Unseen operating condition stability is to be ensured. Coordination, again, multiple AI agents. So that are the research challenges in a renewable dominated grids. Lot of this area is having a lot of research scope. So future direction is multi-agent reinforcement learning or coordinated fax control. AI assisted wide area damping control using phasor measurement unit measurements, digital twins for controller training and validation, hybrid AI plus model predictive control, grid forming inverter and fax controllers in renewable grid systems. These are the future research directions in renewable dominated grid, which probably new researchers or faculty members who are interested in doing their PhD work in the area of renewable can take up this particular area. So definitely it is going to have a very important prominence in the near future. So this is all my presentation, and thanks to your patient listening. So if anything is to be added on, yes, coordinator can just take it up.
Thank you, ma'am. So participants, any queries? So I think there are no queries. So thank you, ma'am, for such an insight and engaging session. We sincerely appreciate the time and effort you have taken to share your knowledge with us. On behalf of the Department of Electrical and Electronics Engineering, I extend our heartfelt gratitude to you. Thank you once again, ma'am, for being with us today. We look forward to interacting with you again in the future. Thank you, ma'am.
Okay, by this we can wind up the day one of our FDP. Once again, I thank each and everyone who gathered here. Let's meet tomorrow for the day two of FDP. Okay, thank you.
The feedback link for session 2 has been posted in the chat box. Please complete it.
The feedback form will be shared in the WhatsApp group also.
Oh, I'm sorry. My net connectivity got lost, and so I had to. I was pushed out of the platform. Okay, am I audible now?
Yes, ma'am. Yes, ma'am.
Yeah, I'm sorry for that. Okay, my
It's okay.
presentation is over. Any doubts are there? So you can ask me, or you can bind up also. Because I know all teachers, after having a day long work in college, it is very difficult to sit beyond 8:30, and also that is why I also wanted to wind up quickly. Anyway, if you have any doubts, you can feel free to talk to me.
As we come to the end of today's session, we extend our heartfelt thanks to each one of you for your active participation. We look forward to your continued participation in the upcoming session. Thank you and good night.